Okay, today we're going to start a new topic, reinforcement learning. We're going to spend about a week talking about this reinforcement learning problem. So this is a completely new type of learning problem that we haven't seen before. So it's unlike supervised learning and unlike unsupervised learning. And RL really has kind of a flavor of its own to it. So it's kind of its own corner of machine learning. And so we'll spend the next few lectures getting into the details of this RL problem. So a couple of announcements. Homework 4 due tonight, so hopefully you've all made pretty good progress on that. The final homework for the course, homework 5, is going to be released by Monday. As always, you'll have 2 weeks to work on this assignment, and it's due June 9th on the final day of class. It's a pretty short assignment on clustering, and this assignment is short on purpose because you guys do have a final exam and a project coming up, so hopefully it should be a pretty quick homework to wrap up the quarter. Speaking of the final exam, I will discuss the details of that next week. It's going to be a similar format to the midterm, but of course you'll have more time to work on it. Yeah, expect details about that next week. And of course, no class on Monday since it's Memorial Day, so don't show up to the lecture hall unless you want to hang out. I won't be here for sure. Okay, so today we're going to do an introduction to reinforcement learning. What is an RL problem all about? Then we're going to see a really simple, concrete example of a reinforcement learning problem called the multi-armed bandit problem. And then after that, we're going to start talking about Markov decision processes. And these Markov decision processes are kind of a general framework for formalizing reinforcement learning. And so let's get started. So in reinforcement learning, we have a totally new type of learning problem that we'd like to tackle. And the idea here is we have some kind of agent, some kind of decision maker out in the world, represented by this brain. And what this agent can do is that at every time step over the course of some time horizon, it decides on some kind of action to take. So the agent does something. This agent then is interacting with some kind of environment out there in the world. And after taking this action, it observes the state of the environment kind of as a result of whatever action was taken. The agent then potentially receives some kind of reward from the environment. And the goal of our agent is to take actions over time that are going to result in the highest total reward. So our agent is something out there that wants to make money or survive, or is an animal and wants to reproduce or something like this. It's some kind of decision maker interacting with the world. And the other aspect of a reinforcement learning problem is the environment itself. So this is kind of the things external to whatever agent we might be thinking about. So this environment essentially is going to execute the action in some sense. It'll compute the next observation in the sense that the environment gets updated after the actions we take. And it also kind of computes the reward. It's what returns something to the agent itself. So there's this kind of iterative loop where the agent takes actions, the world responds to these actions, and our agent then observes the new state of the world after taking these actions. So in general, reinforcement learning is a very hard problem, where the goal again is the agent to take in some history of states and actions and rewards and try to predict what's the best action for me to take next in this environment. This problem is hard because, well, unlike supervised learning, we don't have any sort of labels or targets that we're directly trying to predict. We only see these kind of indirect rewards, and these rewards might not be all that, well correlated with the actions we take. So the agent needs to somehow figure out what the best actions are. They're not provided as training data, this is a good action, this is a bad action. The agent really needs to go out and explore the world, try things, and see what does and what doesn't result in good rewards. Another reason reinforcement learning is very difficult is that the feedback your agent gets is often very delayed from the actions that it takes. So for example, if you're playing a game of chess and your agent is trying to learn the rules of chess, trying to win, well, you only get rewarded at the end of the game of chess, right? You either win or lose. And sort of all of the intermediate steps of a game of chess, well, your agent, if it doesn't have any prior knowledge about the game, has no idea how well it's doing. So this reward, this feedback, is often very delayed from the actions that we take. There's kind of a long time horizon here, and your agents need to be able to kind of think long-term and plan. In reinforcement learning, our data often also has a sort of temporal or sequential aspect. where in contrast to, say, supervised or unsupervised learning, where we have just a big box of data from the outset and we can build an algorithm based on that, our agent is really interacting with some environment over time. So our data isn't just given to us up front, we really have limited data and we need to sort of spend time collecting that. So we'll need to have techniques that are able to handle this kind of sequential aspect. And another aspect that makes reinforcement learning hard is that the environment itself is actually changing over time. And in particular, the agent's actions often have an effect on the environment. So in this chess playing example, the environment might be like the state of the board at any particular time. And this changes as the game plays. You are playing against someone when you're playing chess, and so this environment is going to change based on whatever they decide to do. So your agent needs to be able to sort of adapt to changes from the environment that might be unexpected or might be hard to deal with. All in all, reinforcement learning can be thought of as a sequential decision-making problem where you're taking actions again over a course of a long sort of sequence of events. And oftentimes these actions that you take have very long-term and hard-to-predict consequences. But in general, it might be better to sort of sacrifice short-term rewards for very long-term benefit. So for a couple of examples of very real-world instantiations of this, well, buying Apple stock 20 years ago, you knew you need to pay a little bit of money then to make a lot of money now. So you kind of sacrifice in the short term to make a lot of money in the long term. You might, in a similar vein, go into debt to go to college. So you make a sacrifice to eventually get a degree and hopefully a job afterwards. And another very relevant example is maybe starting on a course project earlier rather than later. So you sacrifice a Friday night by getting part of your project done, but the long-term benefit is you don't have to pull an all-nighter in finals week. So, lots of examples of this in the real world where, you need to think long-term about the actions you take because they have very long-term consequences. And one kind of aspect of general intelligence, if we're trying to build a very general intelligent agent here, is this ability to plan far into the future. So you need to think not just about how my action is going to, reward me in the short term, but also how this is going to affect me in the future. So all in all, these things make reinforcement learning problems very difficult. Okay, let's talk a little bit more about what I mean by an agent. So an agent is any kind of decision maker. Could be an algorithm, could be a brain in a vat, it could be an animal or something like that. But the agent takes in a sequence of observations, it observes the environment over time, it receives some rewards from this environment over time, and based on this history, needs to decide what action to take next. So you can kind of think of as an agent as like some kind of function, right? Some black box function that's somehow making decisions based on the history. However, there's lots of different choices on how we can sort of decide what action to take next. So there's lots of things to consider here. Like, for example, can I completely ignore the observations out there in the world? Maybe my decision maker, my agent, is just making random decisions, basically. And for some problems, maybe this works fine. Is it enough to just look at observations in the world, Or do I also need to think about, okay, what is the action that I took previously? Maybe I need to take into account what I did in the previous step to decide what I'm going to do next. If I'm looking at the observations from the world, is it enough to just think about what happened in the last few time steps? Maybe the last 3 observations or something like that? Or do I need to really account for all of the observations I've seen so far? Do I really need to think about what happened 10 years ago to decide what I'm going to eat for breakfast tomorrow? So there's lots of different ways you can kind of combine the information you're taking in from the environment in order to decide on what actions to take. This leads us to the notion of an agent state. So I'm going to use capital S sub T to represent the state of an agent throughout these slides. And sort of intuitively, you should think of an agent's state as what's sort of the agent's mental model of what's going on. It's kind of their internal representation of the world. So the agent's state is some kind of computation that it does based on the observations, rewards, and actions that have been taken previously. So if we observe our environment over T steps, taking actions, we can define a notion of a history. And this history is simply everything that has happened so far. So, for example, our history up to time T might be an observation, O1, it might be a reward, R1, and then it might be a subsequent action, A1. Well, then this loop just repeats for the next time step. I get an observation, a reward, and an action, so on and so forth, up until the current time, t. And based on this total history, so I have an observation and a reward up to time t, I now need to decide what action I should take, a sub t. But the agent state is something that we're kind of free to choose as sort of AI designers here. So the state is what the agent is going to use to decide on its next action. So for a very simple state, the agent's kind of internal mental state could just be, okay, what's my previous observation? I'm going to ignore the reward, I'm going to ignore my previous actions. The agent state could also be something, okay, what is the previous observation I saw and what's the previous reward I got? Maybe if I see the world behave in some way and I got a positive reward, that'll influence what action I'll be taking. Or we can look, at the previous action I took as well. If I'm trying to decide how to drive from point A to point B, maybe I have some route planned in my mind and I want to consider, okay, I turned left here, so I need to turn right here. Or we can go further back in history and look at, say, observations from the previous 4 time steps or something like this. So states are very, very general. The idea, again, just being, what is the agent going to use to decide on the actions to take? And generally, our state is some kind of function of the history. So it's a very abstract, general way of putting what I've been saying. But I'll point out here that whenever you're designing one of these RL algorithms, really it's up to you to decide what state you want to use. So there's lots of freedom in how you set these up. Okay, and then the next notion I'll introduce is that of a policy. So I'm going to call pi a policy. And what this does is I'm going to take in my current state, the agent's current mental sort of internal representation. I'm going to pass it through this function pi, which is my policy. And this policy returns the next action. So a policy, what I mean by that is just what's the mapping from my current state to my action? What do I decide to do next? You could have a deterministic policy where the action my agent is going to take is just some function of the state. So if I see the current position of the chessboard, well, I know exactly what move I'm going to take next. It's determined by my policy pi. But I could also have a stochastic policy. And what I mean by that is that my policy doesn't return a single action to take next. It actually is going to return a distribution over possible actions. So maybe if my chess playing agent is not very confident about what the next move should be, it should say, okay, maybe I think 80% chance I should move this piece, but 20% chance I should move this piece. So stochastic policies let you kind of encode uncertainty about the next action you might like to take. And in general, a good policy is one that's going to lead to a large cumulative reward. Again, we're not interested in the reward at a particular single time step. We really want that long-term reward to be maximized. So that's what I mean by cumulative reward here. And of course, a bad policy is one that doesn't lead to very much reward at all. So this is kind of the very general RL setup. And over the course of the next few lectures, we're going to see lots of very specific examples of how you set these problems up and how you can actually get agents to learn what actions to take. But let's look at a few examples of actual RL problems out there in the world. So a really nice one is learning to play the game of Go. So in this type of RL problem, game playing, your state, your internal representation in your agent, might be, say, the location of all the pieces on the board currently, and it might also be, say, the history of the last few board positions. Your actions, of course, are fairly simple. It's just what piece should I place where in the next step. I don't play Go, so I might be saying that wrong. And your rewards here are some positive reward if you win the game and a negative reward if you lose. And so one thing I'd like to really point out here is that the rewards are very sparse, right? You might play a game of Go for an hour, and then only after that hour of playing get a positive or a negative reward. So it's very difficult to learn how to play Go because your reward signal is very sparse. It's only coming to you after you make potentially hundreds of moves. And so the agent somehow needs to figure out what moves were good, what moves led to a win, or what moves were bad, what moves led to me losing. This also is a good example of a problem where sort of early actions, maybe the first few moves I play, can have huge consequences on the outcome hundreds of moves later. So there's sort of long-term planning and long-term decision-making that needs to be played here. Okay, you might also want to use reinforcement learning to try and get rich. So here we're trying to design an RL agent to play the stock market. Our state might be something like the prices of very, very many stocks on today's date and the current time. But you might also want to consider, how much money do I have in the bank? How much can I spend on buying new stocks? And you might also have some additional market data coming from various sources. So the state here can be something quite general that we take into account when we're deciding what actions to take. Our actions, again, fairly simple, just what stocks should I buy and sell at, say, every morning. And our rewards here are no longer just, +1 if I win and -1 if I lose, but maybe our reward is proportional to how much profit I make. So this illustrates that the way you set up the rewards can kind of take into account how good you're doing, not just necessarily am I doing good or bad. Okay, you might also want to learn how to fly an autonomous drone. So again, our states here might be something like the location and orientation of my drone, the velocity. It could be things external to the agent as well, like the current weather. And the actions here is, okay, how should I move each of my 8 propellers in order to, achieve a particular goal? Maybe I get a positive reward if my drone successfully flies from point A to point B, and some kind of negative reward if my drone crashes. So robotics in general is a really great example of RL problems. We might also have some agent that we want to train to learn how to walk. In this case, the state can be very, very complex. So it could be the velocity and orientation of my agent in general, but also can be the position of all the joints in my agent here. So on the right side, I've got a GIF of a simulation, obviously, of some kind of humanoid creature learning to walk. So not too many joints here, but you could imagine having a real-world robot where there's like hundreds or maybe even thousands of these joints that we somehow need to learn to move in sync in order to achieve fluid motion. And the actions, of course, is how do we move each of our joints in our robot or in our simulation? And again, the rewards might be something like a positive reward if you don't fall over or if you reach some kind of goal or some kind of end state that we're interested in, and a negative reward if you fall over. Okay, just another cool example of an RL agent that actually learns how to climb over obstacles here by, they didn't give him arms, so I guess he's just jumping over them, but you can do quite complex things with reinforcement learning. And again, this is all sort of purely exploration-based. We never tell this agent what it needs to do in order to learn how to climb over these walls. It discovers this by playing around with the environment and failing a lot. A cool example, also game playing, is maybe playing Atari games. But here the state is not just the observation of the board, the state is actually just pixels on a screen. So here the agent has very, very little information about what these pixels even mean from the get-go. We never tell it that it's playing a game, it just sees a bunch of basically bright lights on a screen, and it needs to figure out, by using various actions, here moving the joystick around or pressing buttons, what those actions do. So moving my joystick moves my character or something like that, pressing buttons does some other action. And the reward here might be something fairly complex, like computed based on the current score or the number of lives you have left in this game, and so on and so forth. So again, the agent, when it starts out, has no idea what it's even trying to accomplish here. It just knows I need to get a high score somehow. And just through trial and error, essentially, it will discover ways to do this. Okay, here's a cool demo. Let me see if I can pull it up. Okay, so in this demo, you're going to see an actual reinforcement learning agent learn how to play the Atari game Breakout. I won't play the sound, but as I said, your agent really has no idea how to play this game from the get-go. And so after 10 minutes of training this agent, so 10 minutes of real time just having your agent play this game, the algorithm learns at least how to kind of move towards the ball, but it's really not playing the game all that well, It's kind of guessing at this point still. So it, as you can see, learns to move towards the ball, but still definitely struggling here. Okay, so after 2 hours of training, so not very long, our agent actually has figured out how to play this game. So if we watch it play, does pretty good, probably better than I could do at this game. And again, this is just purely based on sort of exploring, playing the game over and over, seeing what strategies work and what strategies don't work. And what's really cool is that if you train this agent for even longer, so now 2 hours rather than just 1 hour, or I guess 4 hours, sorry, it actually learns a really cool strategy to beat this game. So rather than kind of just playing it as, maybe an amateur would, it learns that it should put the ball behind the pieces, which we'll see in a second. And so it's totally figured out like basically a cheat code for this game where it does super well using this new strategy. Which is really cool because just based on pure exploration, it really found this very effective strategy here. Okay, so this Atari game playing example is actually really great because in recent years, these game playing examples have driven a lot of reinforcement learning progress. And in fact, there's a really cool agent by DeepMind, I think, that actually learned to play all Atari games. So you have a single agent that can play every single game, and in fact, I think it does better than every human player at this point. So yeah, if you're planning to be an Atari pro, rethink that career. Okay, so any questions on RL in general before we get to some details? Yeah. Yeah, so the question is like, how do you tell the agent what actions it can take? This is very problem domain specific and oftentimes requires a fair bit of engineering. So like for that Atari game example, well, we as the AI designers know exactly what it can do. It can move the joystick and it can press the buttons. And so when you set up your agent in code, well, you explicitly give it that set of actions. So you have to tell your agent what actions it can take. Yeah.
When we think about the reward that working with the scenario, right? Like for example, the Go game,
Mm-hmm.
the reward, right? The reward is only like at the end of the game, right?
Right.
So the history wouldn't necessarily be action reward or action observation reward. That word, it would be like reward 1 to 1 at the end, right?
That's right, yeah. So the history as I wrote it was like observation, reward, action. Your reward you could kind of encode as nothing to fit into that. So you potentially get a reward at every time step, but not necessarily. Or you could see it as a reward of 0. You didn't get anything at that time step. Yeah. Okay, so let's look at an example of a reinforcement learning problem called multi-armed bandits. And this is really kind of the simplest RL problem, but it's a good one to have at least seen. So a multi-armed bandit problem is the following setup, where we have capital K different slot machines, which are called bandits because apparently that's what they were called in the 30s or something like that. But we have a bunch of slot machines, and at each time step, we have an agent that can choose one machine to play and receive some kind of random payout from this machine. But each of these machines has some kind of unknown average reward, which I'll call theta. So theta sub I is the average reward for the ith machine. Importantly, the payouts here are random. So maybe 30% of the time the first machine gives me $1, and the remaining portion of the time the machine pays out nothing. And the goal of my agent here is to figure out which of these machines has a high payout and which of these machines does not have a high payout. At the kind of outset, our agent has no idea what machines are good, what machines are bad. It's totally blind to what's going on here. So our agent must somehow balance between playing machines where we know a lot about the reward, maybe we've played them a few times, and if there's a machine we think has high reward, we want to play that machine a lot, we want to make money off of it. This is called exploitation. Oops, I think I did the second bullet first. Okay, so this is exploitation. If you have a machine where you know the reward is high, you want to play it often. But we also want to play machines where there's very little known about this reward. This is often called an exploration phase. And so in RL in general, there's this kind of trade-off between these two, between exploration and between exploitation. So we need to explore the environment to figure out what actions are good, but then we want to actually use those good actions to get rewards. Okay, this probably seems like a totally made-up example, but in fact, lots of real-world problems can kind of be characterized abstractly as these multi-armed bandit problems. So a really good example is online advertising. I have a sequence of K ads I could show to a user. Which one of these ads is the best ad? You know, what should I show my users to get the most clicks? So my first machine is going to be, okay, a user comes to me and I show them the first ad. The second machine is, okay, a new user comes, I'll show them the second ad instead, or something like that. And the reward here might be something like +1 if a user actually goes and clicks on that ad, and 0 if the user does not click on the ad. Then the average reward for each ad, or each machine, is just what proportion of users clicked on this ad. So again, at the outset, we don't know which of these ads is better than the others, so we need to do some kind of exploration to figure out what ads actually get people to click on them. But then once we find out what ads are good, well, we actually want to serve those ads so that we can turn a profit. Another example is something like clinical trials in medicine. So we've got a bunch of medications for a particular, say, disease. I'm going to figure out which of these medications is going to result in the best health outcomes. So here our rewards might be something like +1 if a patient is cured from taking this medication, maybe 0 if the patient's health doesn't change after taking it. It's kind of a null outcome. And maybe a -1 if this drug has really bad side effects. So we can set these rewards up in a very flexible way. And again, here the average reward over many trials is going to summarize how often this drug is either helpful or harmful. Okay, let's see how to kind of phrase this multi-armed bandit problem as a reinforcement learning problem. The actions are, of course, which arm to pull at every trial. The state that we're going to maintain in our agent, again, we're free to choose this as the AI designers, is the agent's current estimate of the average reward per arm. So my state at time t, s sub t, is going to be a k-dimensional vector. So I have one dimension per machine, where the first dimension is going to be what I call theta hat 1, second dimension is theta hat 2, so on and so forth. And these theta hats are essentially the agent's estimate of these true unknown average rewards. So for example, theta hat j, the estimated reward of arm j, is going to be the total reward I received from pulling arm j, divided by the total number of times that arm j was pulled. So it's just sort of a simple average. What have I seen on average as my reward from playing this particular machine? And again, our agent is going to play these arms, play these machines across capital T trials. So maybe I'm going to pull these 1,000 times. And the goal of my agent is to somehow maximize my total reward over these 1,000 trials. Okay, let's see a couple of strategies we can employ to try and solve this multi-armed bandit problem. I'll point out here at the very start that in each of these strategies, what our agent is going to do is going to pull an arm, get some kind of reward, and then make sure it updates its state vector after every trial. So we see some reward and we want to update our belief about the averages. Okay, our first strategy is an awful strategy, but it's a good baseline to keep in mind, which is just random guessing. So at every trial, I'm just going to randomly pull an arm. This, of course, is not very smart. We're not adapting to choose the arms that we've seen that give high rewards. And it's all explore, no exploit. So don't recommend doing this one, but it's something you can do. And let's see, anyone have any ideas of what I could do besides just random guessing here? Yeah. Keep on doing ones that I haven't done before. Okay, so if I have 1,000 trials and I have 2 arms, well, I'm just going to randomly pick them. Well, I think we're back in strategy 1 if we do that. So yeah, other guesses. Maybe from people we haven't heard from very much. Yeah, sure. Yeah. Yeah, so that's the answer I was looking for. So strategy 2 is explore, then exploit. So we're going to fix some number s smaller than our total number of trials. And for the first few trials, we're going to just pull random arms. So we're just going to explore, see what arms give us high rewards. And after our first S trials, well, whatever arm has given us the highest reward so far, we're just going to pull that for the remaining T minus S trials. Okay, this was supposed to be another question, but what is wrong with this? Well, usually you don't want to explore for too long, right? You don't want to spend all of your time randomly pulling arms. So you want S to be fairly small in this strategy. But what can happen is you can get pretty unlucky and choose a suboptimal arm. You know, maybe I only explore for 20 trials and just by chance, one of my bad machines got sort of lucky and gave me high reward. So this can often choose to leading a suboptimal arm if we first explore and then exploit. Okay, so let's see a third strategy. Any guesses on what I can do that's better than explore than exploit? Yeah. Yeah, so that's essentially the strategy still, though. Like we're always pulling the best arm, and then if it goes below some threshold, it's no longer the best arm, then we would switch to the second best arm at that point. So we're still doing sort of explore first and then only exploitation afterwards. So we can do a little bit better than that still. Yeah. Yeah, so I think that's an advanced way of doing what I was looking for, my third strategy. So my third strategy here is called epsilon greedy. And the idea is rather than doing pure exploration and then pure exploitation, what I'm going to do is I'm going to mix these two together sort of randomly. So what I'm going to do is I'm going to fix a number epsilon between 0 and 1. And this number epsilon is going to represent sort of the probability with which I'm going to explore. So what I'm going to do is at each trial, I'm going to pull the best arm. I'm going to do exploitation with probability 1 minus epsilon. And then with probability epsilon, I'm just going to pick a random arm. And this is going to be my exploration step. So here I'm randomly mixing together both exploitation and exploration. Here this parameter epsilon really explicitly is giving us a handle, kind of a knobbed tune that trades off between exploration and exploitation in this problem. This is a number that needs to be chosen by us. It's a hyperparameter of the model, but typically it's pretty small, somewhere like 5 to 10%. If it's too large, then you're spending too much time picking random arms. If it's too small, you don't explore enough. Usually this strategy is going to do a lot better than sort of the explore first, because we're continually exploring the arms that we maybe don't have as much information about. So we mix in some sort of short-term risk by picking a random arm for potentially very long-term rewards. Okay, let's see another strategy. This is very similar to epsilon greedy, except it's now called epsilon decreasing. Here we're going to fix two numbers, an epsilon between 0 and 1, and some number alpha between 0 and 1. Where here alpha I'm going to call a decay factor. And at each trial t, what I'm going to do is I'm going to pull the best arm with probability 1 minus epsilon times alpha to the t. So what I'm essentially doing is I'm taking my epsilon, my exploration parameter, and I'm shrinking it over time. So epsilon times alpha to the t is going to essentially give me exponential decay of this epsilon term. And the idea here being that when t is small, when I've only played a few trials of my arms, I want to do more exploration. I don't know very much about my arms, so it's a good idea to just kind of try more random ones. This corresponds, of course, to a high epsilon. But when t is large, I've already spent a lot of time kind of playing my game. I know which of my machines are good and which are bad, so maybe I don't want to do so much exploration anymore. I just want to exploit the arms that I've already found to be good. And so this is a strategy that can kind of give you some improvement over that epsilon greedy strategy. There's a whole lot of more strategies out there for this multi-armed bandit problem. We're not going to cover them all here, but these four are really the simplest ones. Okay, let's look at an example. So let's say that I've got 5 slot machines, each one having some probability of giving me a positive reward +1, and some probability of giving me a reward of 0. So here, pretty much all of my machines are bad, except for my third machine, which has a pretty high probability of giving me a reward. And what I'm plotting here is on the x-axis is the number of steps that my agent has taken, so how many trials it's done. And on the y-axis, I've got the average reward per step. So higher is better, we want more reward. And what we can see is that the choice of epsilon in this epsilon greedy strategy can have a pretty significant impact on the average reward that my agent sees. So for instance, this kind of pink dotted line here is that pure exploration strategy corresponding to just randomly picking arms. We can see this gets a very low average reward, just randomly choosing arms is obviously not a good thing to be doing. But for fairly small values of epsilon, like say 5%, this orange curve, or maybe 10%, this green curve, the agent is really maxing out its reward by spending a good sort of balance between exploration and exploitation. Okay, here's another example of this decreasing epsilon strategy. And what you can notice here is that, say I set my initial epsilon to be 0.2 or something like that. And so for various values of alpha, this decay rate, we see again similar looking curves. Note here that alpha equals 0.9 is this dashed blue line down here. So a small value of alpha means fast decay. And so because alpha is pretty small here, 0.9, kind of our exploration decays too fast. We don't spend enough time exploring. But for larger values of alpha, like 0.9 and 0.999, we see pretty good results. Interestingly, this red line here, an alpha of 0.1, or rather 1.0, corresponds to not decreasing epsilon. So we're doing epsilon greedy, no decreasing for the red curve. And interestingly, this decreasing epsilon strategy results in higher average performance, shown in these green and orange curves. Another really cool feature of this decreasing epsilon strategy is that the agent is able to more quickly learn what the good arms are. So here it takes something like, say, 50, 100 steps for the agent to really figure out what arms are good. But in this strategy here, it often takes on the order of 200 steps for the agent to figure out what arms are good. So this is just to illustrate that the strategy you use in this kind of problem can have pretty significant impacts on not only the speed at which your agent finds good actions, but also kind of the overall value of the actions that it finds. Okay, so this is pretty much all we'll say about multi-armed bandit problems. It's again a really simple example of a reinforcement learning problem that can really model a lot of real-world applications out there. So showing ads, where to place ads, website design, medical trials, all kinds of things can be phrased in this type of problem. And in general, it's an alternative to massive A/B testing, where you have multiple alternatives you're trying to compare. Again, you need to really balance exploration against exploitation because your agent needs to discover things about the environment. Multi-armed bandits are actually a fairly deep topic, despite just being about slot machines. There's lots of nice theory about there proving bounds on what's called regret. And this regret is essentially a measure of how far away your strategy is from an optimal strategy. So if you're interested in this, there's a nice reference I've put in the slides here, and you can check it out. So any questions on multi-armed bandits? Okay, cool. So let's go ahead and talk about Markov decision processes now. So I mostly wanted to talk about multi-armed bandits just to give you guys like an example of what a real concrete RL problem looks like. But now we're going to kind of talk about RL problems in sort of higher level of generality. In particular, we're going to phrase things in terms of these Markov decision processes, but it's going to take us a little while to get there. There's lots of stuff we need to build up first. So in today's lecture, we're going to talk about just Markov processes, what these are, but eventually we'll add in rewards to these Markov processes and get Markov reward processes, and then eventually we'll also add in actions to these to get Markov decision processes. So we're building our way up to this sort of general framework for RL. Okay, so the key property that we're going to make use of here is what's called the Markov property, or the Markov assumption. And what this property says is that the future is independent of the past given the present. So in other words, if I know what happened right now, well, that's sufficient for me to tell you what's going to happen sort of in the future. I don't need to account for all of the things that happened previously. And we'll see plenty of examples of this. So it seems a little abstract now, but it'll make sense in a bit. So a little bit more formally, a state S sub t is a Markov state if the probability of ending up in a new state after one more time step, given the current state, is exactly the same as the distribution over future states conditioned on the entire history of the states. So in other words, sort of distribution about what the future is going to look like in the next time step, I can determine that based on just the previous or the current state. I don't need to look at the full history of what happened. Again, we'll see examples of this. For Markov processes, we can really characterize them using what's called a state transition matrix. So if I start out in some kind of state S, and I have some kind of successor state S prime, i.e. what state I'm going to be in at the next time step, the state transition probability, P sub S, S prime, is what's the probability that my next state is S prime, given that I'm currently in the state S. And again, using this Markov assumption or Markov property, knowing the current state is S is kind of sufficient for me knowing this subsequent state S prime. So these state transition matrices, P, really tell us transition probabilities from whatever current state I might be in to whatever state I might be in the future. So it's a, say, n by n matrix if I have n different states in my example. And it tells me, okay, P sub 1, 1 is what's the probability that I'm currently in state 1 and I stay in state 1. P sub 1n is the probability that I'm currently in state 1 and I end up in state n after one step. Of course, each row of this matrix needs to sum to 1 because they're probability distributions. Okay, let's see an example. So this is the so-called student Markov chain. Our states here are kind of what a student is currently doing. So they might be in class 1, class 2, class 3, and their state at the end of the day might be whether or not they pass this class. We've got another state for sleeping, another state for going to the pub, and one for being on Facebook. So if you can't tell, this is an old example because we've got Facebook here and not something else. So in any case, we've got a bunch of states that our student can currently be in. And our student can kind of transition from one state to another state with some kind of probability. So maybe I start out by going to my first class, class 1. Well, I have a 50% chance of going to class 2. That's what this 1/2 on the arrow between these guys indicates. But then I also, if I'm in class 1, have a 50% chance of just heading on up to Facebook. But if I'm in Facebook, well, I have a 90% chance of staying in the Facebook state, and only a 10% chance of going back and paying attention to class 1. We could say the same thing for class 2. Okay, well, maybe after my first class I'm tired and there's a 20% chance I just give up, go home and go to sleep, and an 80% chance I go to class 3. I guess by class 3 it's late enough to drink, so you might head to the pub, and so on and so forth. So in all of these states, I have some probability of transitioning to some kind of different state. And again, these probabilities depend on the current state and the state that I'll be transitioning to. So as I've shown it to you, I've given you all of these possible transition probabilities. But usually we don't really know sort of a priori what these probabilities are. We might know the states, we might know what state can go to other states, but we don't know these transitions. And the way we can sort of estimate these transitions for a Markov process is we can sample what are called episodes from this Markov chain. So what we're going to do is we're going to start our student at state S sub 1 being C1, corresponding to class 1. So I start my student out by going to class. And maybe I simulate this chain. So I observe a student over the course of several days. So they go to class 1 in this first example, they go to class 2, they go to class 3, then they pass and go home and go to sleep. So this is an example of a single episode of this Markov chain. And note that these all end in sleep because once I'm in this sleep state, I don't transition anywhere else. I guess I just stay asleep. In a second day, maybe my student wakes up, goes to class, goes to Facebook, and then on Facebook once again, returns to class 1, goes to class 2, and says, okay, I'm skipping class 3 today, I'm going to go to sleep. And so on and so forth. So we can sample multiple sort of episodes of a particular Markov chain, and then using sort of the each step transitions, estimate these transition probabilities. So all in all, I'll make a matrix where I have sort of one row per state and one column per state. And then each number I fill in is, well, okay, with what frequency did I start in class 1 and end up in class 2, for example? So it would be 0.5 here. Or what frequency did I sort of start from class 2 and transition to class 3? It should be 0.8, and so on and so forth. So again, Markov processes or Markov chains are kind of ways of capturing transitions between particular states. And because of this Markov property, we don't need to consider the full history. So if I'm currently in class 3, well, I don't need to know that I was in class 1 and class 2. There's just some probability that I'll go to pass after this. So So the transition at each step only depends on the current state here, and not any kind of history. Okay, looks like we have time for another demo, so let's go ahead and do that. Okay, so this is a fun little demo of Markov chains. So here we've got just a two-state Markov chain where your states are A and B. So at every time step, my agent, or my current state, is represented by this black dot. And what you can see is that it transitions between these two states, A and B, at every step. Note that there's loops on A to itself and from B to itself, so we can kind of stay in a state for multiple time steps. Down here, we've got the same sort of state structure. So there's a probability of going from A to B, vice versa, and staying in the same state. But we can play around with these transition probabilities. Again, these transition probabilities tell us how likely it is to go between particular states. So maybe I want to say, okay, if I'm in state A, I want to make it very likely that I stay in state A. So what you'll notice is if I increase this parameter, well, I'm kind of stuck in state A now because I've made this 1. If I decrease it a little, it'll eventually get unstuck from here. So you can kind of play around with these and kind of see that we can model sort of very different behaviors with these Markov chains. Okay, let's look at kind of a real-world-ish example of a two-state Markov chain. So maybe I have some kind of weather data where I'm just interested in whether or not it was a rainy day or a sunny day. So my rainy days are represented by R's and my sunny days are represented by S's. So every day is a new time step. I wake up and see, is it sunny or is it raining? And kind of qualitatively looking at the draws from this Markov chain, we see that the sunny days tend to be kind of grouped together. You know, we might have multiple sunny days in a row, and the rainy days also tend to be grouped together with multiple days in a row. If we kind of just randomly pick a random day or a sunny day, trying to simulate this behavior, trying to model it, well, it doesn't look at all like the draws from our actual sort of weather distribution. You know, this simulation down here doesn't look anything like our simulation up above. But what we can do is actually sort of increase the probability of staying in a same state. So these are kind of these self-transition probabilities. And in doing so, we can better model this kind of stickiness behavior of weather. Okay, so play around with that on your own. It's kind of fun to look at the animations. Okay, so let's go ahead and wrap up for the day. So again, we've seen Markov processes, and these are processes that really only have states involved with them and some kind of transition probabilities between them. But as we've been discussing about reinforcement learning, well, we also want to be able to incorporate rewards into these kinds of things, and then eventually have agents that don't just get randomly moved from state to state. They should also be able to take actions that determine what kind of states they end up in. And so we're building our way up to these more general processes. Okay, and then just to wrap up for today, we saw reinforcement learning, a very kind of general introduction, where again we have some kind of agent interacting with an environment over time, and they need to explore this environment to maximize their reward. We saw multi-armed bandits and a few strategies of how you might solve these problems. And then we lastly introduced the notion of a Markov process, where again the next state only depends on my current state. These are of course characterized by these transition matrices. Okay, so any questions? Okay, if there's no questions, we can wrap up for the day.